Good to go? Thank you very much, guys. Hello, everyone. Hope you're having a good day so far. Lots of interesting talks today, and yeah. Thank you for joining us today. It's a lot bigger turnout than I expected, but today we're going to be talking about embracing complexity, which might ring some alarm bells in some of your heads, but we're going to try and understand entropy in software design and how that helped us solve a really important problem at Aviva. Before we get started, quick round of introductions. My name is Shivam. I work on the platform and security team at Aviva Zero, and I have a background in distributed systems and cloud engineering, and this is my colleague, Pete.
Thanks, Shiv. Hiya, my name is Pete. I'm a senior software engineer here at Aviva Zero. I'm currently the cloud engineering team lead, and in a past life, I was a consultant, and I used to work as a software engineer at a company called Arm, which you might have heard of, the silicon company based in Cambridge. So, let me also make a quick round of introductions to the project we both work at, Aviva Zero. Zero is a greenfield cloud-native platform that delivers motor insurance products through price comparison websites, or we sometimes call them PCWs for short. So this is our, like we've already mentioned, our first time here at GopherCon, and we're very excited to be here. If you've heard of us, it will most likely be because you've tried to actually buy car insurance and probably come across us in one of these price comparison websites up on the screen. So you would have more likely heard of Aviva. That is the UK's largest general insurer. Aviva provides insurance, investment, and a suite of other financial services. Zero is very much a part of Aviva, but we specialize in offering schemes to offset the emissions of the miles that you've driven on top of your car insurance. So, as from the last slide, Zero is a greenfield insurance platform, literally built from zero, pardon the bad pun here. But this is important because the insurance industry, as you might imagine, is rather old and has historically been a bit slow to adopt new technologies. And specifically, Aviva is one of the UK's oldest insurance companies. It's around about 300 years old. It has its roots in the Hand-in-Hand Fire and Life Insurance Society, founded in 1696, and also the Norwich Union, as you can see up on the screen here, which was founded in 1797. So with that in mind, essentially Aviva wanted a new challenger to the motor insurance fray, and that is how the concept for Zero was born. So we started the planning of Zero in the spring of 2021. In July that same summer, the first line of code was cut and first commit was pushed. And within about 7 months of really busy coding, we went live in February of 2022. So that's actually a really quick turnaround time. And since then, we've absolutely gone from strength to strength and delivered many new features to the project since then. These days, we're well over 500,000 customers, and we're approaching 1 million in sales. Come on. All right. So how did Go help us get there? Now, I realize this isn't really the best slide we've ever made, and I just really quickly wanted to point out that this is supposed to be a gopher silhouette, but I now realize it looks like a gummy bear, which isn't fantastic. But so anyways, back to Go. Why Go? So as all of you in the room probably will know, it's blazingly fast, and that means fast compilation times and really fast performance, especially with Lambdas with cold starts in the cloud. Another thing I really like is the Go ecosystem. It's reached a level of maturity that's higher than other high-performance languages out there, namely, let's say, for example, Rust. Actually, as Cameron from the keynote speech this morning mentioned, Go also has really great dev velocity, and it's really easy to be productive very fast. Another thing I quite like about Go, on a similar sort of topic, is the gentle learning curve it has. It's quite simple, actually, to use very powerful features like concurrency, and we use this quite extensively for parallelizing our API calls. On top of that, it has great library support in AWS's SDK and CDK. This allows us to define our infrastructure as code as well as our application code all in the same language. Oh, no, too early, sorry. Most importantly is probably the community. And being here today is a perfect example of this. The Go community and support for one another is going really well in London, and this is a great example, and we're very glad to have the opportunity to participate in an event like this. Cool. This is a slide I wanted to show you guys. So here's a bit of a snapshot of the tech that we use. So let's start with the easy one up at the top. Can I use this laser? Yeah, there we go. So we love Go here. And all of our backend are Go microservices. We also have a really big culture on teaching Go. So lots of new starters were really keen to get their hands dirty with Go previously, but hadn't quite had the chance to. And I can actually speak for that because I had a really great experience learning Go on this project. Another thing to quickly shout out here, actually. So in the top left-hand corner, there's this library that we use called Temple in Go. Can I have a quick show of hands to see how many people have heard of Temple before, please? That's about a third of the room, I'd say. That's quite good. So we're the first production use case for Temple. And for those of you who don't know what it is, it's a templating framework for Go. It was founded by someone called Adrian Hesketh, who actually, funnily enough, also designed our initial architecture. He also spoke here last year at GopherCon on a talk for language server protocols. OK, moving on. There's another big item here I would like to point you to, and that is AWS. So we're cloud native in the sense that all of our services were designed to be run in the cloud, namely, specifically AWS. We take full advantage of all the serverless offerings that AWS offers us, and this comes in the form of the fact that most of our compute is in Lambdas. Again, Go is great here with low latency cold starts, and again, shout out to the great library support with SDK and CDK. I'm actually also going to plug this talk that I'm interested in seeing tomorrow. It's called Go for Serverless Functions from Solaris, and it's going to happen in this exact same time slot tomorrow. So back to serverless functions. We use it in tandem with EventBridge and SQS, which powers our event-driven workflows. Up next, and again, Next.js and React front ends we have are distributed and live as ECS tasks in our AWS estate. I'm going to point you to Snowflake here as well. We do use DynamoDB for our core transactional data, but we offload our data into Snowflake for our analytical workloads. Our code lives in GitHub, as well as our deployment pipelines. And lastly, and probably quite important for later in the talk, we use a trunk-based development flow with feature flags to power continuous delivery. And recently, we started using the feature flag management tool called LaunchDarkly. But again, more on that later. Cool. Let's talk a little bit about Zero's business model. So most motor insurance is commonly sold through price comparison websites. The customer will visit these PCWs, and they will find a variety of insurance products depending on their parameters. If those parameters match the footprint that we sell to, will be an option for them. So this means that we get our customer traffic by plugging into these PCWs, and we can decide on how much of the market we want to serve to win new business. The market comes to us rather than us going to the market. And I find this a really interesting prospect for a software project. And that's kind of because a lot of the other software projects I worked on in the past would require quite a large sales department or a marketing department to be able to tap into the sort of user ecosystem and build up their user base. Whereas we actually just have a tap that we kind of can turn on and off and scale to as we like. Cool. So when a quote gets accepted and paid for in our new business journey, it becomes a policy. Now, as an insurance company, our central data model is the policy. A policy as a concept can be updated and renewed any number of times until it gets cancelled, as you can kind of see on the screen. Let's take a little bit of a deeper dive into what that looks like. A policy is just a JSON object at its heart. Some of the information for a new policy, as you can see here in the example we've provided, can be things like the policyholder name, which is over here. I'm trying to be stable here. Mrs. Jane Bloggs, or the car that is insured, which is the Nissan Leaf, a very eco-friendly option. Over the life cycle of a policy, it may be that it's updated into new versions through a variety of different ways, and one of those ways could be changes from the customer. So we call these midterm adjustments, or MTAs. And that could be something like changing the vehicle. And in this example, in version 2, we've updated the car to be the Toyota Prius. Also another eco-friendly option, but it is worth noting that we sell to a wide range of vehicles and has nothing to do with necessarily just the eco-friendliness of the vehicle characteristics. So other types of MTAs include adding or removing a driver and changing your address, for example, and so on and so forth. Other ways in which you can update a policy will be things like if a customer has unfortunately had an accident and would like to make a claim, then we will reflect that into the insurance policy. And Finally, renewals. Should the customer decide to stay with us, we generate a new policy version for them in the new term. So now that we're comfortable with the idea of a policy, let's move on.
Thank you, Pete. Much to your dismay, we can't talk about insurance all day, so we'll start talking about a bit of mutability and what that means in practice. So policies are mutable, as we've talked about, with all the adjustments that we just discussed and more. But mutability in practice actually has quite a few issues. And that mainly comes down to safety with concurrent access, data integrity, and really important for us as a really regulated environment is auditability. So we actually model all of our policies as a set of immutable versioned items and keep track of changes in between them. That gives us some safety with regards to all those issues, but doesn't mean you can't shoot yourself in the foot when you're making changes to a policy. You still need a really structured way to approach that. What we really want is a mechanism that tells us exactly what adjustments we can make, how we can make them, and whether or not they're valid in line with our business parameters. That's where policy diff comes in. It's a library that we wrote in the early days of Zero that encapsulates all of that logic. The way we do these adjustment changes is a little bit different to what you might expect. When we apply adjustments, we actually start with the target state on hand. And we don't just do a direct update. What we have to do is calculate the differences between those policies, get them in something we call a diff, which is a set of deltas or adjustments, and then systematically apply them to the base policy to bring it into a new version. You might be interested in why we do that, and it's a little bit counterintuitive to understand, but it's not the main topic of this talk, so trust me when I say it's the right decision. Now, this worked great for us for a really long time, but we eventually ran into some problems when we started modifying the library, or when we wanted to modify the library. And to kind of give you an idea of what those problems are, I'm just going to walk you through how you might use this policy diff library. As we talked about, we're going to start with two policies. In this example, we're going to walk through a renewal process. So when you're up 30 days before your renewal date, some of you might have experienced, you're able to make changes to your cover. And what we do is we generate a quote for the next term of the policy. A quote is the same underlying data model as a policy, it's pretty much identical. And we allow the customer to make changes to this during this renewal window. When we want to transact that renewal, we need to take that desired state that the customer has told us about, calculate the differences, see if they're valid, and apply them onto the new term of the policy. To do this, you call this function diff policies. It's fairly straightforward. Give it the current policy, you give it what you want it to become, a few options that aren't too important at the moment. The result of that is this diff structure, and this is an aggregate of all the adjustments you have to make on that policy. It stores the base policy and a set of adjustments that you need to apply to get into the new desired target state. There's an implicit interface to this diff structure, and besides allowing us to do a couple checks, retrievals, it exposes two main methods, apply and validate. The idea is that you generate a diff by comparing two policies, and that gives you a set of adjustments or deltas. What you need to do is apply these in a certain order to get into the target state. Once you've done that initial differential, it's a two-step process. We want a validation, and that lets you know whether you actually can do that change or not. And if not, we get a set of issues that we can read into, perhaps trigger some side effects or communications to let the customer know that we can't actually do what they want. You then apply the adjustments, basic mutation onto the policy, but we've kind of structured it in a particular order so we don't step on the toes of other adjustments. But here's the first issue. Why would you ever not validate this change? And there's no reasonable scenario that we could think of where you don't validate the diff to a policy. But we found that in tests across our entire stack, people often created their own set of adjustments to take a policy through its life cycle to simulate a natural policy. And that's fine. That's a valid use case and something that you might want to do, but we don't want to risk our production services running through unvalidated adjustments just because we need to do it in tests. Yes, it made it easier, but it was at the cost of adding uncertainty to our interface. The important bit here is that your API is not just a mechanism into the underlying system that you're trying to use. It's a prescription or a suggestion. It tells you what's OK to do. And in this case, it kind of tells us that it's OK to skip validation because it's something that you choose to do. That's not what we want as the writers of the interface. So we need to be careful about making these kinds of suggestions at every turn. So moving on with our usage, you might also be interested in the individual adjustments, and you might want to walk through them and pattern match and do computations of side effects depending on what kind of adjustments you've got on the policy. And looking closer at exactly what an adjustment is, we can see it's modeled as an interface, which is a really important part of the issues with this library. Knowing what I just explained about an API being a suggestion and not just a mechanism, you might rightfully wonder, didn't we want to strictly govern the adjustments that can be made? And that's one of the reasons we wrote this library, to make sure that we've locked down exactly what we can and can't do to a policy. But when you export an interface type in a library, what you're essentially saying to the consumer is, feel free to make your own concrete implementations and pass them through. And you might not think about that when you're writing your code, but we actually ran into this issue where a bunch of unchecked adjustments just floating around the system and different systems didn't recognize them. We don't actually want anyone to do this, so again, it's an implicit suggestion that we don't want to make. We should have thought about it in the first place. And this is a demonstration of what actually happened. We had a communication service that was responsible for determining what communications send out to customers. And we had these adjustments that had been defined outside of the scope of the library that were flowing through, unrecognized, and the service didn't know what to do. However, just like that validation with the diff, there was a reason for this approach. It was the simplest implementation. It was the path of least resistance, especially because adjustments typically have a few things in common, and we had cases where you wanted to simply generically iterate over them and pattern match against key common attributes. And at first glance, it seems like a really great use of abstraction. It was to represent adjustments as an interface that satisfies the largest adjustment defined. And more importantly, everyone at the time, when the company was a bit smaller and the team was a bit smaller, knew how to not completely mess up when we had this system out there. But when you have complexity and freedom like this, you have to make sure that you distribute that knowledge as fast as you grow, so everyone knows what to do and what not to do. But you could just not allow that to happen in the first place. Use concrete type instead of an interface. That's something we'll talk about a bit more later. Another thing to point out here is that looking at the actual interface for the adjustment, whilst these live on the diff, and you'd expect to use the diff to do the application like we showed you earlier, you could just do it on the adjustment as well. You can apply it directly to a policy or validate it with respect to a differential. And that's kind of annoying because now we have multiple different ways to approach the entire workflow. You could generate a differential, grab the adjustments from it, and then use the differential to apply it, or go through them on your own, skip the validation again, apply them on their own, or just don't do a differential to begin with. Just collect your own adjustments and apply them as you wish. That last one is a little bit valid because sometimes when we generate those midterm adjustment quotes that Pete was talking about, we do use this library to generate those adjustments. But regardless, we have 3 ways to go about doing this entire workflow, all of which let you either skip the systematic application or the validation of the differentials. Again, no reason to do this in practice. This completely disregards everything that we as the writers of the interface want the consumer to think about and do. This last one's a bit nitpicky, but the interface really overgeneralizes many adjustments. You see a few of these methods accept a policy, and policy is a huge object, well over 100 fields, and all of these adjustments have methods such as these, checking if the adjustment affects the policy's pricing, getting a summary and getting a humanized summary. Most of the adjustments don't actually need that policy object on it. And fair enough, there's no performance overhead. The compiler will neatly optimize these out, but it's a bit of mental overhead and bloat that we just could do without. This is something that our head of engineering famously is called Spooky. It's some code from the diff policies function that we looked at earlier, and it sits nested in a few different function calls. The critical bit here is between lines 3 and 5, where if we don't have an ID for an insured person, which is represented by that insured object there, we generate one for them. And that's fine. We actually don't want insured objects on a policy to not have an ID, but the key bit here is that this is not where you'd expect that to be set. The semantics of this diff policies function suggests that you just pass it to policies and get the differences back, but you actually end up mutating some of the arguments that you pass in. It's completely uncertain whether or not you'll get the same things back as you put in there. And this bug, when we were working through it, took a few years of my lifespan and made our head of engineering very
Great. Thanks, Shiv. Let's talk about what actually happened. So to paraphrase that corny Silicon Valley idiom a little bit, when you move fast, you break things. And as a consequence, the library had become quite difficult to maintain, and the knowledge of how it worked and the goal of what each component and decision behind those designs became fragmented. And also the intended usage patterns were also, in some cases, completely lost. These factors became quite important when we started approaching scaling. This library is crucial to quite a few different production services, but it's very focused around just a single product and that single product's business parameters. When we started talking about how we'd like to add something new to the mix, one of the biggest obstacles was basically trying to figure out how the diff library should be altered to support something like that, whatever that might have been. And basically, all of the issues we just looked at with Shivam and more prevented us from having the confidence to start making changes to the library. So the usage patterns bit was particularly important. There was no clear way to interact with it. We had defined an interface, but one without a rigid contract dictating how to use the interface. So we had to ask ourselves this. How can we make changes with confidence without knowing if our changes would violate that contract? Or indeed, without knowing or being comfortable with the idea that each function might not even live up to its own semantics, henceforth that spooky action that our head of engineering hates. Additionally, and probably quite crucially, you might have noticed that I sort of broke my promise of not talking about feature flags a bit later on, but I didn't. But here we go. So there's an absence of any reference to feature flagging so far. And this is because, unfortunately, this policy diff library isn't compatible with our release system. And you might ask why, but the reality is this library was built before we introduced feature flags into our SDLC. So we couldn't even make changes deep inside the library with the safety of knowing that our changes were incremental, individually deployable, and testable chunks. And all in all, the difficulty and complexity of adding new code and making new changes was just incredibly high. So, to summarize, for implementation simplicity, we have generated interface complexity. So, how might we strike this balance? Let's take a little bit of a break, zoom out a bit, and hear Shivam talk about entropy.
Thanks. So we've covered a bit of that wishy-washy software engineering philosophy, a bit about what your interfaces mean and what your functions tell the user. But now let's do a brief physics lesson, talking a bit about entropy. So entropy is a concept with roots in thermodynamics. And its discovery is widely attributed to someone called Rudolf Clausius. He's a physicist and mathematician who first proposed that in any irreversible process, such one that doesn't naturally return to its original state, in a thermodynamic system, any system with energy in it, heat will always dissipate out into its surroundings, becoming lost to disorder, unavailable for use by the system. The entropy of that system has increased because its energy has become less usable. This idea has evolved and morphed over the years to generally become a measure and concept for disorder and chaos. And we won't dive in too deep about all those empirical measurements and interpretations, but there's a few important properties that we should discuss first. The main one being that entropy naturally tends towards a maximum. And what that means is, unobstructed, the entropy in a system will always increase. And this leads to a few interesting phenomena. For one, Clausius describes entropy as the reason that we can distinguish the past from the future. Just really deep philosophical stuff, but it also explains really simple things like why ice melts, why metal rusts, or why gas fills up the room that it's in. Or a bit more magnificently, why eventually everything that exists and everything you've known and ever will know will dissipate into nothing. Just like that. But before that happens, I want to talk about air conditioning. When it gets really hot, the entropy of the thermodynamic system, that is, for example, your home, is very high. The particles in that room, they have really high kinetic energy, they're moving around quite a bit really fast, and there's lots of ways that they can organize or disorganize themselves. So maybe you decide to install an AC unit, and this cools down your home, bringing that kinetic energy down and lowering the entropy of the room. But to do that, you've actually caused an increase in entropy in a lot of different places that you might not even think about. For one, your AC is probably powered by electricity, and a good portion of that is going to come from burning fossil fuels. Now, what burning fossil fuels does is takes low entropy chemical energy in the form of fuel or coal or any other kind of fuel, and it turns that into waste sound, heat, and releases gases and fumes that are all high entropy states. That electricity needs to get to your home somehow, and that happens through the power grid, which also itself releases a bunch of waste heat. And that doesn't even include all of the heat and sound produced by your AC unit, and then also all the entropy increases from building the power stations and the power grid and building your AC unit. Those are still being amortized every single day. And all of that is to reduce the heat in your home by just a few degrees. I'm not trying to shame you on your energy usage or anything, but I just want to highlight that this is not a zero-sum game. You'll notice that all of those entropy increases are much greater than the decrease that you experience in your home. And that's due to a second property of entropy, which is that for a local decrease in your system of entropy, you need to provide an even greater increase in other places. So,
yeah. Well, thanks, Shivam, for bringing down the energy in the room. Or should I say the entropy? No, I'm joking. So let's see what this might mean in software, bringing it back. Well, entropy has its roots in other fields, along with physics, like chemistry, information theory, and even in software engineering. While they don't all closely follow the ideas of thermodynamics exactly, it still maintains its general properties and the general notion of it being a measurement of disorder. So in software engineering, we can define entropy as the gradual increase in complexity and disorder within a code base as changes are made over time. So to start with, your code base is in this initial state, the green bit over here. And that implies a sort of low entropy state because the code base is empty. As we add new features, fix bugs, make modifications, the code can become more tangled, harder to understand, and more difficult to maintain, thus yielding higher levels of entropy. I'm sure the developers in the room will understand. What this means is every change you make increases the probability that something you don't want to happen just might happen. But hold on a second. What actually is complexity? And how is that different from the word like complicated? I mean, it's actually part of the title of our talk. And now that we've kind of built up the context, let's make sure that this word is well understood. Oops, that's too early. So as our head of engineering, Ed, very often likes to remind us from the Cynefin framework that was developed by David Snowden, something that is complex isn't complicated. I won't get into the Cynefin framework, but I'll define the meanings in my own way. But if you are interested in the Cynefin framework, please come to our stand later and speak to our head of engineering, Ed. He has really long hair. So if we consider a problem that we describe as complicated, then there's actually a series of simpler and much more achievable steps to follow so that we can solve the problem when broken down. It's just rather arduous to be able to get there. However, for a problem that we describe as complex, there isn't a series of steps to solve it, and on inspecting the problem, it appears to have disorderly characteristics, which cannot be predicted or broken down easily, if at all. So summarized probably in a shorter way, complicated means that it's difficult but predictable and achievable in an orderly and knowable fashion. Complex means it's difficult but disordered to a point where it cannot be predicted or broken down. So it's all about how knowable the problem is. And because of that, we can say that complexity is synonymous with an increase in entropy. All right, let's come back to entropy a little bit. Conceptual causes of entropy increase, on top of what I said about the progression of a code base, can be things like quick fixes. So that is adding patches or quick fixes without a proper refactor. We sometimes call this tech debt. So a bit of a throwback to applying the adjustments directly without any validation, or probably even worse, skipping the validation entirely in that entire diff. There's feature creep. So continuously adding new features without considering the overall design. Again, an example of this for us is adding new adjustments without considering, again, the overall design or the wider business requirements that were at play. Knowledge silos, they happen. So this happens when you move fast and you don't distribute the knowledge quite fast enough. And this can make the code quite hard to understand. And this is especially necessary when the interface usage patterns are already not clear and complex as aforementioned. Okay, I appreciate that the sentiment of this meme is that Go is sort of the love child between Python and C++. In my opinion, probably more like C. But the idea here is that it emphasizes that there are inconsistent coding practices. Different styles or different approaches used by different developers over time. Not everyone writes idiomatic Go, and that's okay, because they draw upon experiences from different backgrounds. This one is probably a more apt meme, because sometimes we have coding styles or patterns, and they manifest in our Go code base that seem to inherit from, for example, a Java MVC background. All right, let's zoom in a little bit more into the code level, and specifically within a language like Go. Complexity in Go language constructs can manifest itself in the following ways. So there is concurrency patterns, cross-routine communication, and synchronization of Go routines. There are interfaces, generics, type conversions, assertions, and the number of implementations of the interface, and whether we can guarantee their integrity within our systems. So actually, on the topic of generics, I spoke to another one of the speakers, Jesus, who gave the talk on the Go runtime earlier today. And we talked about how sometimes people would abuse generics a little bit for the kind of argument of, just in case we need it. And obviously, that introduces quite a lot of uncertainty by the nature of generics and unknowability, which yields higher entropy increases. And finally, reflection, and that implies that there is a reliance on types that are uncertain at runtime.
Yeah, so we've seen a few interpretations and representations of entropy, but we're focused on interfaces specifically for the time being, and the idea of having a high or low entropy interface. There's a few ideas that we can put forward here. For one, we can posit that a high entropy interface lacks clarity over its usage. There's multiple ways to achieve something, and there's no indication about which one is the better one. It's kind of like us having those multiple ways to apply an adjustment to a differential or to a policy. You could do it with the diff, you could do it without, you could sort off the entire thing and just mutate it directly, and there's no clear way to tell you how to do it. Also, we might say that higher entropy systems or higher entropy interfaces leave a lot more room for consumers to do something that is not intended, or even worse, do something to harm both themselves and the provider of the service. For us, this was also, again, the sort of ability to skip validation and apply adjustments individually and unchecked, because not only did this mess with the internal operations of how that entire library worked, but if you wrote a service that consumed this and started passing it garbage, then you're going to break your services too. Another thing is higher entropy interfaces might shift more control into the hands of the consumer, allowing you to provide custom implementations. And this is fine, but only if you can guarantee compatibility and safety with the rest of your system. When we saw the suggestion of creating custom adjustments and passing them into the diffing library, we couldn't guarantee that those adjustments were valid and in line with our business parameters. So we can't just open up our system to that and allow people to just create whatever they want. In essence, higher entropy interfaces host a lot more uncertainty. And more often than not, uncertainty is the root of all the problems that we have in software. It means that you can't say for sure that something you don't want to happen actually doesn't happen. And maybe even worse, it tells us that we don't know the full range of outcomes from a particular process. Following the laws of entropy that we looked at earlier, the only way to tackle that uncertainty is to increase entropy elsewhere. And in our case, this usually means the complexity of the implementation. Now, that might not be intuitive, because I'm sure many of you think that you've written really non-complex implementations and non-complex interfaces, and you're really proud of it. But I'd like to shoot you down just now and tell you that this isn't a zero-sum game. That complexity has to live somewhere. If it's not living in your interface, it's not living in the implementation, then it's living somewhere else in your stack. Whether it's using neat language constructs, the ones we talked about earlier, reflection, generics interfaces, different kinds of compiler trickery, or maybe if you use a language like Python, you get so much of that syntactic sugar that lets you do interesting things without fully understanding what's going on underneath the hood. It's there. There's no avoiding it. Either you push it to your consumer, or you push it to your dependencies. But following that other law of entropy, that increase has to be greater than the local decrease, the cost to wherever you push it to is going to be greater than the cost that you incur. So not only should we consider how uncertain or complex an interface to some kind of system is, but also what's out of sight. Our usage of abstractions and other people's code can sometimes lead to issues. sometimes not knowing how your workload is actually being executed and what's really going on behind the scenes can cause problems. Not always, and definitely not majority of the time, but it can cause issues. And that's what we saw with that sort of spooky action in the diff library where we were doing mutations that you weren't aware of. And understandably, abstraction is this cornerstone of software development that we all have learned about, and building things in layers that don't depend on other layers. But sometimes it's led to people being almost dogmatic about always embracing abstraction and not worrying about what's going on in different layers of that stack. So instead, again, sometimes, definitely not always, it can be worth embracing increased implementation complexity in the right places. By collecting that complexity into your domain, you could potentially get the best of both worlds, where you have a really clear, information-rich interface, and also visibility and control over your implementation. You're not using too many abstractions that you're unaware of or could potentially have side effects that you're unaware of. You're kind of also relying on the fact that whoever's code you're using has gone through the same thought process and made sure that their interface is clear, doesn't have side effects. But as we know, people are not infallible, and they make mistakes. And this ties in closely with an empirical measure of entropy called, skipped so many there. This ties in very closely with an empirical measure of entropy called fan-in, fan-out complexity, and that has roots in electrical engineering, if anyone studied that in university. It leans into this idea of the relationship between the number of dependents you have and the number of dependencies you have. In our case, it's about the complexity on your dependent side and the complexity on your dependency side. A super uncertain and chaotic sort of relationship with your dependents combined with a really chaotic relationship with your dependencies is a recipe for disaster. But this has downsides, namely that now you take on all that chaos, and you've got to write this, and it's your headache to write this complex code, maintain it, distribute the knowledge around it, and generally just keep it up to date and working and ensuring all the semantics are also on point. I understand why a lot of people don't want to do this. It's a lot of work. You finally have to do your job, and that sometimes people can't handle that. But let's talk about how we restructured our complexity. Could you tell us a bit more, Pete?
Yeah, so actually, before I get on to that, let's quickly recap on what we've already talked about. So we've already talked about our policy structure, the diff library, and the problems that it had. We also talked about entropy and complexity and how that exists in that policy diff library, or interface, sorry. And finally, we're going to finish on what we did to restructure our complexity for the betterment of our project. So firstly, we turned it into a service. I'm hoping everyone can read that, because we made that bigger, because the meme wasn't quite big enough. As we briefly mentioned earlier, many services depend on the diff library. Many crucial services depend on the diff library. And if each service were to have different versions of that library, it could spell trouble for us, especially in production. We do have dependency automation in place in the shape of Renovate. But it's not perfect, and it leaves room for error, especially human error. So we decided to turn the library into a RESTful service instead. This means that the core logic for our library is now rolled out atomically to all consumers at the same time and not individually deployed to each consumer. Come on. And then we worked on a brave, new, lockdown interface with specific and controlled usage patterns. So we've condensed out the bits that make it a bit of a HTTP service, but these are the two main methods you'll interact with as a consumer of the service. So diff policies is largely the same as it was before, but we've added some context to it now. Apply adjustments previously didn't exist as its own method, but now we have it as its own function. It accepts a base policy, an effective date so that we can enforce the same date for all adjustments, a set of adjustments as a new type, and notice specifically that that is not a slice, and we'll touch on that with Shivam in a second. Oh, and also some options. Now, I'll let you guys have a quick look at this, but the eagle-eyed engineers in the room will probably see that we return an error in the function signature, but we don't actually have code to report that. Just to reiterate, we've taken out a lot of the code just to simplify this for you guys. So as before, you'd start with diffing two policies. In this additional layer, all we really do is call the underlying function as it was before. What happens afterwards is more important. So here, we do a mapping of old adjustment types to new ones under this from legacy adjustments function, which is an important part in consolidating our interface. Crucially, we always validate here, no matter what. The consumer doesn't get a choice. We will roll out a testing library for use and tests at some point, but for the time being, anywhere that's followed that pattern of not validating, we'll have to just figure out another way to do it. Maybe be a bit more verbose and complicated for those consumers on their end, but it significantly helps us out in production. And next, we take advantage of the fact that this is now a HTTP service. Nothing on the client's end gets mutated, so we can give them a hand by just applying the changes and returning the updated policy back in the response. Most common usage patterns of this library is just get the diff, apply the adjustments, and we can just do it here from the API. This is the response returned to the consumer. So pretty much some of the same fields as they were before, the validated bool, the issues, the old and the updated policy. But there's actually something new here. So let's take a closer look at that policy adjustment set type that you can see here with Shivam.
So before, adjustments were modeled as a generic interface, and a set of adjustments was just a slice of those interfaces. But we saw loads of issues with that, mainly to do with being able to provide your own concrete implementations and how this messed with the system. So in this new layer on top of the library, what we do is make the adjustment set a struct containing concrete adjustment types. That means that this type, the policy adjustment set, is a single source of truth for what adjustments you can and cannot make to a policy. It tells you what's valid, and you can only ever apply adjustments by putting them in this struct and then passing them on to the apply adjustments method. So we've successfully locked down that bit of the interface to prevent rogue adjustments. That comes with some uncertainty, mainly this stupidly big switch case statement that maps new adjustments to the old ones. That's all of that is only half of it, so yeah.
If that.
If that, yeah. So using things like generics and interfaces, it mitigates that relentless verbosity that a lot of people don't like. I don't like it. I don't like this. But we've gone the complete opposite way by making everything concrete. Interestingly, we didn't do away with all the ergonomics that we got from having it as a generic interface. You know, as you mentioned, a lot of the patterns, usage patterns that we used would iterate over that set of interfaces and get specific attributes that existed on every single policy. Then you could do computations or pattern matching on them and figure out what you want to do next. And we still wanted to facilitate this because it was a bit too tedious to go through every single usage and pick out the exact policies we need or exact adjustments we need. So we tried to maintain that a little bit. We set up this new adjustment interface that has this common method that returns these 4 fields that we guarantee to be on every single adjustment. But how can we guarantee that? And how can we walk through that struct and provide all of those adjustments as this common interface for people to use? This might make you a bit nauseous, but we use this init function that runs at the beginning of the package load. I think this is a really neat way to solve the problem, despite all the issues that we might see with init functions and the sort of hidden sort of complexity that it adds to usage. But what we do here is run some reflection to check that every single field on a struct implements some interface. And for us, it's looking at every single field on the policy adjustment set and making sure that it satisfies the adjustment interface. This is a little bit complicated, so no need to read the whole thing, but what we do here is take out the struct type and the interface type, and then sort of recursively walk through every single field, make sure that if it's a slice, then the underlying type is satisfying the interface. If it's a pointer, then the underlying type is also satisfying the interface. And doing this at the init level and panicking if it goes wrong is essentially the sort of type check that we couldn't get at compile time because we wanted to express all our adjustments as the concrete types. If you have a better idea, please feel free to come to the stall and help us out with it. But this works pretty well, and it's sort of a risk that we're willing to take. Now let's just do this. So we have this all adjustments method on the adjustment set that returns a slice of adjustments, and we use that function we just showed you earlier to walk through every single field and recursively pick out all of the nested or sliced up adjustments that are sitting on there, return them as their generic format. And adding this complexity, this init logic and this reflection, and it's a little bit tucked away, but we've gotten the best of both worlds here in some sense, where the developer ergonomics is still there, but we still maintain the concrete types of the adjustments, and we only allow retrieval of the common fields as their generic interface. But we also, we also maintain all of that safety that we have. So we have ergonomics and safety at the cost of all of whatever this is. Let's look at the apply adjustments function. It's not too complicated. It's largely the same as what we had in the diff policies function. We use that stupid switch case to convert all of our new adjustments into the old ones. And we pass in that effective date field to kind of consolidate that relationship between them. We generate a new diff using the underlying library, and we go ahead with that forced validation. Again, you don't get any say in whether it gets validated or not. We make you do it, and then just apply the adjustments to the policy in the end. Another benefit we have, touching back on that feature flagging bit, is that now this is set up as a service. We can inject dependencies in the client. We can add this feature store, and we can propagate it to different levels of the library. And that lets us make changes to the underlying library when we choose to do that in a way that is rolling out small chunks of individually deployable and testable units. And for fun, there's also a logger in there.
So you might ask what happened to the entropy after all of that. So let's summarize. One great benefit now is that, we mentioned this before, but the atomic rollout of changes to all consumers at the same time. New changes to policy diff will now update at runtime since it's a service. So we don't really have that problem of managing it as like a code level dependency anymore and having things fall out of sync potentially. But this does come at the slight cost of maintaining it as a physical service. So there's a bit of a complexity increase elsewhere in the project. On that same note, actually, changes can now be feature flagged, which is great. That means that brings policy diff in line with the rest of our SDLC, making the change management process less complex. Although I haven't actually mentioned it yet, but feature flagging it implies that it's now stateful, meaning sometimes we could have complexity in the behavior of the service. But we're kind of happy with that because we have the ability to iterate with feature flags quickly, and that's much preferred for us. And besides, we're kind of already used to using feature flags by now, so it's not a huge extra burden to us at all. Another thing is that the rules of engagement have been clarified for the interface, and that's a really big win for us because we've gained information on its usage. But as Shivam showed earlier with that really big, ugly implementation details and stuff, there's now this new layer of types and code logic in the implementation, and that leads to a bit of complexity now to the developer. Yeah, cool. Consumers are now less likely to shoot themselves in the foot, basically, because the usage complexity has been reduced. So we can't just directly apply an adjustment. We actually are forced to take that policy through the lifecycle properly. Although some consumers will have to use more verbose patterns, that will increase the complexity for those consumers specifically. We've still kept some of those great developer ergonomics in the form of the ability to iterate over that adjustment set. But as you've mentioned, it comes at the cost of that init function and that complex reflection that we have to do.
So let's try to visualize that a bit in the form of scribbles again. Initially, we had this chaotic implementation, and we had an even more chaotic interface. The entropy was high in both these things, but more so in that interface because so many ways to do things, so many ways to do things wrong, and a lot of ways that you could really mess up things for everybody involved. Now what we've done is added this layer in between, this wrapper that maps a new interface that we built to the old one, and it does a bit of consolidation in between. Even though we've added this new bit of complexity, and in total from the system we have higher entropy due to all this additional logic, the reflection, the init function, the things that are out of sight, where we really wanted it to be sort of concise and certain and low entropy is the interface, and we achieved that. So it was about where we targeted our complexity in the end. That low entropy interface lets us do a lot of really interesting things. This is just the first step in solving a problem. You might have noticed that we actually didn't even touch the underlying library at all. But now that we understand our interface really clearly, we can build up from it because we know it works. We know how everyone's using it, and we have this sort of strict, rigid contract that we can be confident about whether we're breaking it or not when we make changes. We can now add feature flags. This is really important to us because it means that we can make these small changes and deploy them individually, test them individually, and even potentially in the future do things like A/B testing if you wanted to. And that means when we do the changes that we planned for the underlying library, and there's a lot of them, we can do it smoothly. Before, we didn't know what we were doing. We didn't know what we could potentially break. We didn't know exactly what our consumers needed from us. But now adding that additional layer in between, taking that complexity into our domain and that uncertainty with all that logic we added, we can do that. And that concludes that.
And that just about wraps it up. So thank you very much for listening to our talk. Thank you. Before we move on to questions, I just really quickly wanted to say that if you're interested in more information about Aviva Zero or our talk, or you just kind of wanted to hang out with us because we're cool like that, we have a stall in the main room. We're on the far side. We have donuts, okay? So please come find us if you want donuts, and in the downtime between talks. We'll still be here tomorrow, so thank you very much.
Okay. Thank you. Okay, do we have any questions? Anyone?
Oh, I think we're on.
Yeah, okay.
Hello. Is this on? Yeah. Great talk, guys. You mentioned all of the different adjustments that you've got now. What would you have to do if the business needs have changed and some of those adjustments are no longer valid?
Yeah, good question.
Mm-hmm.
So before we kind of had the benefit of having generic, it's kind of tucked out of the way and we could just remove things if we wanted to. But now that we have them sitting on that concrete type, we have to take a bit more of a formal deprecation process. But fortunately, we can use the Go documentation and mark those fields on the struct as deprecated. Again, with the feature flagging, we can also decide when and when not to apply those adjustments if we wanted to. So that's how we'd approach that moving forward.
Cool. Are there any other questions in the audience?
Anyone else?
I think everyone just wants the donuts already.
Thank you for coming, and have a great rest of your day.
Yeah. Thank you.
Yeah, thank you.